there, this is mass and mole conversions. Chemical formulas and equations are expressed in terms of their number of moles. So you'll remember balanced chemical equations from grade 10. So a formula like this, 2 CAs plus O2 plus 2 CaO, actually reads as 2 moles of Ca, calcium, plus 1 mole of oxygen, making 2 moles of calcium oxide. So those coefficients are actually a mole relationship or a mole ratio. But we can't count the number of moles of something because you can't see individual particles. And remember that 1 mole is equal to Avogadro's number of particles, so you would need a lot of particles before you could actually get 1 mole of something. So instead of counting individual particles and instead of counting by moles, what we can use is mass, because mass is something that's really easy to do. We have an electronic balance that we can bring into a lab. We can put a sample of material onto that electronic balance, get a mass, and then from there we can actually convert it into number of moles, and then down the road we can also turn that into number of particles, atoms, etc. So that's where we're going to go with it. The atomic mass on the periodic table is actually the mass for 1 mole of an element. So we actually call those values molar masses, and the symbol we use is capital M. So if we're looking at our periodic table, and let's do an example. Let's say, for instance, if you had 1 mole of boron, if you go to the periodic table and look at the atomic mass, it's 10.811. That's the mass of 1 mole of boron. It would have a mass of 10.811. You can see that all of the masses are different because the atoms are different. As the atoms get bigger and they have more protons and neutrons, a mole of them is going to weigh more as well. So for instance, if you had 1 mole of chlorine, it would weigh 35.453 grams. So if we have a compound, then what you'll do is you'll put the molar masses of the individual elements together to combine them for the molar mass of the overall compound. So let's try that on for size. Our first example here is, what is the molar mass of calcium iodide? So the first thing we need to know before we find its molar mass is we need to know what the formula looks like for calcium iodide, so we know how many of each individual ingredient we're going to need here. So let's do our crossover rule, and we can use our tools from Unit 1 to help us here. We have that overview sheet on nomenclature that we can get out to help us. So calcium is Ca. It's in the second column of the periodic table, so it has 2 valence electrons. It needs to lose those 2 valence electrons to have a nice shell that's full underneath, so it will take on a 2+ charge when it loses those 2 electrons. On the flip side, the iodine is in the 7th column. Its symbol is an I. Because it's in the 7th column, it has 7 valence electrons. It needs to gain 1 more to fill its orbital, so we're going to gain 1 electron for stability. And now it's time to cross over and make our formula. There we go there. So what I want to work out now is, what is the molar mass? So again, the molar mass is the mass for 1 mole. So I'm going to give it the symbol M, capital M. And what I'm looking at is, I want to first find out the molar mass of calcium. So going to my periodic table, I've got 1 calcium atom in the formula, and its molar mass is 40.08 grams. I'm just going to keep 2 decimal places here. You'll find that different periodic tables have different numbers of decimal places. Even 1 decimal place generally doesn't foul things up too badly if you reduce that much. And then I'm going to add that molar mass to the 2 iodines that I have. So 2 times the molar mass of iodine, which is about 126.90 grams. And then I'm going to add that all up, and I should get 293.88 grams. So that's just figuring out a molar mass. The next thing I want to be able to do is I want to find a relationship between masses and moles, because usually we're talking about the moles of things, and so if I know its mass, how do I get it into moles? So let's see how that works. So this is what our mass to mole calculations look like. So we have a new conversion factor. This is lucky number 3. Remember, anytime 2 things equal one another, you've got yourself a conversion factor. So 1 mole is equal to the molar mass. I put in grams here, G here, just so, because when we're setting up our problems, we're always trying to get rid of units we don't want, keep units that we do want. So putting that unit in for molar mass is very helpful. Remember that molar mass can be represented by capital M as well. So down below you'll see where we use our 2 fractions or conversion factors. I've just replaced molar mass with the capital M, a little bit shorter, a little quicker. So we can use this conversion factor in two ways. As usual, we can put moles on top, molar mass on the bottom, so that will allow us to get rid of grams if that's what we want. And then on the other side, we have molar mass on top, moles on the bottom, so we would use this one if we want to get rid of moles. So let's try this first problem together. How many moles are in, oh, let me put a number in here for us. I didn't realize it was missing. There we go. All right, how many moles are in 126 grams of potassium carbonate? So as always, we're going to tackle this problem the same way we always do. Step number one is, what are we looking for? So how many moles? I'm looking for moles. So set up the problem, moles equals. The next thing I always put down is, what do I have? I have one number, 126 grams. Now it's time to put in a conversion factor. The only conversion factor that I have to work with here is this new conversion factor, that 1 mole equals the molar mass of something in grams. So when I use my conversion factor, I multiply it by my conversion factor as usual. In this case, I want my 1 mole on top, because if you look at what we're looking for, I'm looking for moles, so I want moles on the top. And I want that molar mass value to be on the bottom so I can cancel my grams. So I've got a little bit of side work to do here. Over to the side, I'm going to do a little bit of work here. I've already done this once in that last example. What I want to now do is figure out the molar mass of potassium carbonate. First step, as usual, I've got to figure out the formula for potassium carbonate. So using my periodic table, I'm going to look up potassium. Potassium's in column 1. It has 1 valence electron, which is going to lose for stability, so it's going to have a 1 plus charge. We have a carbonate. 8s are on the back of the periodic table, so I'm just going to scan down, look for carbonate. I've got a CO3, 2 minus, so I'm going to do my crossover rule and come up with my formula. So I've got a K2CO3. In terms of the molar mass, I generally am not going to do a step-by-step sort of thing here. I could do it step-by-step, but really all I'm going to end up doing is putting this into my calculator fairly quickly. And that's what I would expect you to do as well. You don't have to show all the work of coming up with your molar mass, just put it into your calculator. So what we want to do is 2 times 39.10. That will take care of the Ks, the potassiums, plus our carbon, 12.01 grams, plus our oxygens, 3 times 16 grams or so. So my molar mass that I'm getting, I'm going to put it right in the problem, I'm getting 138.21 grams. We might have a little bit of difference on those decimal places, again, depending if you're keeping all the decimal places you see on the periodic table, or like me, if you're rounding to 2 decimal places. So we might have a little bit of variety there, but nothing significant. You'll find that at the end, when we do the math here, because we're going to limit the number of significant digits from that 126 grams, you're only going to keep 3 digits anyways. Not going to make a big difference. So into the calculator it goes. I'm going to bring it to 3 significant digits here. So final answer, 0.912 moles. All right, let's try one more. In this case, a reaction produces 0.346 moles of sodium sulfate. What mass is this? So again, set up the problem as the same way as always. What am I looking for? I'm looking for mass. If I want to be explicit here with units, I could also remind myself, okay, let's put a G in there to remind myself that that's the grams, the unit that I'm looking for at the end. Now, same as always, what do I have? 0.346 moles. And then I'm thinking about my conversion factor, so let's write it out over here. I've got 1 mole equal to molar mass in grams. For this particular problem, I want mass on top, so my molar mass value, which I'll find in a moment, will go on top. My 1 mole will go on underneath so that I can cancel it out. And again, now it's time for that little side work on the side. We need to come up with the formula for sodium sulfate, and then we're going to figure out the molar mass for sodium sulfate. So let's do that little bit together just down here at the bottom. So formula first, sodium sulfate. Sodium is column number 1. It's got 1 valence electron. It's going to lose that electron to become a 1 plus. And then sulfate, we've got another 8 here. So we're looking at the back of the periodic table. Take a scan down the list until you find your sulfate. It's going to be an SO4 2 minus. Cross over the values. We've got Na2 SO4. From here, again, you don't have to show all the work for finding our molar mass. You can just do it very quickly in your calculator. I'm going to just talk it out, and then you should be able to get the same value as me. So we've got our 2 sodium, so 2 times 22.99, plus the sulfur, so 32.06, plus the 4 oxygen, so plus 4 times 16. I'm getting 142.04 here. Oh, my dog going. All right, let's get rid of our moles. That leaves us with grams, which is precisely what we want. So let's work the math. Again, thinking in terms of significant digits here, I'm going to actually show you the two answers. So in our calculator, I'm getting 49.1458. Stupid dogs. And then, because the given number here, that leading zero doesn't count, we've got 3 significant digits. I want to bring this value to 3 significant digits as well. So I'm going to cut it off right there. The neighboring number is a 4, so my final answer will just be at 49.1 grams. And of course we have to practice. So the first part is our work with finding molar masses. So pretty straightforward. Question 40 is a little bit tricky, so if you're feeling confident with this homework, you might want to start halfway and work towards the top, the more difficult end problems. And if you're feeling like, let's start from the beginning, I'm not feeling that confident yet, start right back at 31. The second set of questions here are then using my conversion factor, 1 mole equals my molar mass, and working through those conversion factor problems. Good luck!